A particle just proved that reality doesn't exist until you look at it. Not as a theory, not as a guess. In a real laboratory, with real equipment, in an experiment that has been repeated thousands of times and always gives the same impossible answer. A single particle was fired at a barrier with two narrow openings. Nobody watched which opening it went through, and the particle, without any explanation, went through both of them at once. It interfered with itself the way two waves interfere when they cross on water, left a pattern on the detector screen that could only happen if the particle genuinely, physically traveled two separate paths simultaneously. Then someone turned on a detector to watch which opening the particle chose, and the interference pattern vanished completely, as if the particle knew it was being observed and decided to stop doing something impossible. Here is the part that should keep you up at night. The detector didn't touch the particle, didn't redirect it, didn't slow it down. The only thing that changed was that information now existed somewhere in the universe about which path the particle took, and that information alone was enough to change what physically happened. Reality behaved differently because something learned something about it. I've spent years trying to find a comfortable way to explain that sentence. There isn't one. You either sit with the discomfort or you look away. Most people look away. But if you stay with it, if you actually follow the thread of what that experiment is telling us, it leads somewhere that reframes everything. Not just physics, the nature of what exists, the role of observation, whether the universe has a state independent of being perceived. These are not philosophical decorations on top of real science. They are the conclusions that the actual data keeps pushing us toward, no matter how many times brilliant people have tried to find another way out. And there is no other way out. What we are about to explore together is not a collection of clever ideas about tiny things happening in expensive laboratories. It is the structure of reality itself. And to understand how anyone figured this out, we have to go back to a moment when science was so confident in itself, it was almost frightening. Because the crisis didn't come from nowhere. It came from a world that was absolutely certain it had already won. Friends, if this kind of deep dive into reality is something you want more of, subscribe and leave a like. It genuinely helps more than you'd think. Before the particle confused everyone, the universe made perfect sense, or at least it seemed to. For a stretch of time that covered multiple human generations, scientists operated inside a framework so reliable and so elegant that challenging it felt less like open inquiry and more like bad manners. The framework said, everything that exists has a definite position, a definite velocity, a definite future, calculable if you have enough information and enough patience. The universe was a machine, an enormous, intricate, breathtaking machine, but a machine nonetheless. Gears turning gears, forces acting on masses, causes producing effects in clean, unbroken chains. And this wasn't just philosophical comfort. It worked. Planets moved exactly where the equations said they would move. Tides came in on schedule. Engineers built structures that held, bridges that carried weight, instruments that measured time with steadily improving precision. The framework earned its confidence through centuries of correct predictions, and inside that confidence grew something subtle and dangerous. The assumption that knowing more was just a matter of looking closer, that the universe, examined at finer and finer scales, would continue to behave the way it behaved at scales humans could see and touch, that the rules were universal, that the machine went all the way down. And then someone tried to calculate how a heated object glows. Not a complicated object, not a strange material, just any object, warmed up, emitting light. The classical equations were applied. The math was done carefully, correctly, by people who absolutely knew what they were doing. And the answer that came back said the object should be releasing infinite energy at high frequencies. Not a large amount, not an amount that could be rounded up to infinity as a dramatic way of saying very large. Actual, mathematical, structural infinity, which would mean the universe was destroying itself, right now, in a cascade of endless radiation, which was, and this is the technical term, completely insane. The equations were not wrong because someone made an error. They were wrong because the assumption underneath them, that energy flows continuously and smoothly like water from a tap, was wrong. And the man who first noticed a way to fix the math did something that made him deeply uncomfortable. He assumed energy didn't flow at all. It jumped, in fixed, minimum amounts, discrete packets that could not be subdivided. He used the word quanta because he needed a word, and that one fit. And then he spent years hoping it was just a trick of the calculation, a convenient fiction that produced correct numbers without meaning anything real. It wasn't a trick, and somewhere in the back of his mind he probably already knew that. So the trick wasn't a trick. And the moment that became clear, the entire foundation of classical physics developed a crack you could drive a truck through. Because if energy only moves in fixed, indivisible packets, then the universe at its smallest scale is not smooth. It is not continuous. It is granular, like the difference between a ramp and a staircase. From a distance, both get you from one level to another, but up close, one has steps you cannot skip. And that distinction, that seemingly small geometric difference between a ramp and a staircase, turns out to change everything about how reality is allowed to behave. The man behind the calculation didn't want the credit for this. He published because the numbers worked, not because he believed the idea was physically real. He kept hoping someone smarter would come along and show that the packets were a mathematical illusion, a shortcut that happened to give correct answers without reflecting anything true about the universe. Nobody came. What came instead was a young physicist working in a patent office, reading papers on his lunch break, who looked at the packet idea and did something unexpected. He didn't try to explain it away. He took it seriously. He asked what else it would explain if it were actually true, and the answer he found was sitting in a laboratory result that had been frustrating experimenters for years. A result so stubbornly inconsistent with wave theory that most people had quietly stopped trying to make sense of it. The experiment involved shining light onto metal and watching what happened to the electrons inside. And what happened made no sense at all. If you increased the brightness of the light, nothing changed in the way that mattered. Electrons came off at the same energy, regardless of how intense the beam was. But if you changed the color of the light, the frequency, everything changed. Below a certain frequency, no electrons came off at all, no matter how blindingly bright the light was. Above that frequency, electrons popped off immediately, even in near darkness. Wave theory had no explanation for this. Waves should deposit energy gradually, like rain filling a bucket. More rain, fuller bucket, faster. But that wasn't what was happening. What was happening looked exactly like what you would expect if light came in packets, each packet carrying a fixed amount of energy determined by its frequency. Hit an electron with a packet that carried enough energy, and the electron escaped. Hit it with a dimmer packet, and it didn't matter how many packets you threw at it, none of them individually had enough. The bucket analogy breaks completely. Each packet either has the key or it doesn't. And this meant that light, which everyone agreed was a wave, was also somehow a particle, not instead of a wave, at the same time. And that sentence, which sounds like a contradiction, is not a contradiction. It is a description of how light actually behaves, which is far stranger than a contradiction. Because a contradiction is just two wrong ideas colliding. This was one right idea that contained both inside it simultaneously. That realization about light, that it carries its energy in packets and behaves like a particle when it interacts with matter, opened a door that nobody was prepared to walk through. Because if light does this, what about matter? What about electrons themselves? An electron is a particle, obviously. You can measure its charge. You can deflect it with a magnetic field. It hits a detector screen as a single dot in a single location. Except, when you fire electrons one at a time through two narrow openings in a barrier, and you let them accumulate on a screen over time, the pattern they build is not two clusters of dots. It is an interference pattern, alternating bands of many hits and no hits, spread across the screen in a way that only makes sense if each individual electron traveled through both openings simultaneously and interfered with itself on the way. Not some electrons going left and some going right. Each one, both paths, at once. I want you to sit with how strange that is. A single electron, which you can detect as a point, which has a definite charge and a definite mass, travels through two separate openings at the same time and arrives at a location determined by the interference of its two paths with each other. There is no classical picture that contains this. You cannot draw it. You cannot model it with anything from the everyday world. Not billiard balls, not water waves, not anything you have ever seen or touched. The electron in flight is not a ball on a path. It is something for which human language does not have a ready word, something that spreads through space as a wave of probability and collapses to a point only when it finally interacts with something solid. And the physicists who first had to confront this, people who had spent their entire careers thinking carefully and precisely about the physical world, did not find it charming or intellectually exciting. They found it genuinely disturbing, because it meant the question they thought science was answering, the question of where things are and how they move, was not the right question to be asking. The right question was deeper and stranger, and the answer waiting at the bottom of it would force them to rebuild physics from the ground up, on a foundation made not of certainty, but of something that felt at first like surrender. The foundation they built on probability wasn't surrender. It was the most precise thing anyone had ever done. And the first thing it revealed about electrons was so unsettling that some of the people who discovered it genuinely considered leaving physics entirely. Because when you actually look at where an electron is inside an atom, not where theory says it should be, not where a clean diagram shows it orbiting like a little moon, but where it actually is when you measure it, you find something that has no shape, no trajectory, no path. You find a cloud, a smeared region of space where the electron might be, weighted by probability, thicker in some places and thinner in others, but never pinned to a single point until the measurement itself pins it. The early atomic model had electrons circling the nucleus the way planets circle a star, tidy, visual, easy to draw on a chalkboard, and completely wrong. Not approximately wrong, not wrong in minor details, but structurally, fundamentally wrong in a way that made the whole picture useless. Electrons don't travel in circles. They don't travel at all, in any sense that classical physics would recognize. They exist as standing waves wrapped around the nucleus, each wave corresponding to a specific energy level, each level stable, not because something holds the electron in place, but because the wave fits perfectly, like a vibration that finds its natural frequency and just stays there. And the reason this matters beyond the beautiful strangeness of it is that this wave structure is the reason atoms don't collapse. In the classical picture, there was always a fatal problem. An electron orbiting a nucleus is an accelerating charge. Accelerating charges radiate energy. If they radiate energy, they slow down. If they slow down, they spiral inward. The math gave a specific time for how long this would take, a fraction of a second, which meant that according to classical physics, every atom in the universe should have imploded almost instantly after forming. The fact that they didn't was not a minor embarrassment. It was a complete catastrophe for the classical picture. Quantum mechanics didn't patch this problem. It dissolved it. The electron isn't orbiting, so it isn't accelerating in the classical sense, so it isn't radiating, so it doesn't spiral inward. The stability of matter, the reason anything solid exists, the reason you have a body and the chair beneath you has mass, and the air in your lungs holds together at all, is a quantum effect. Take away quantum mechanics and you don't get a simpler universe. You get no universe. Just a brief flash of particles collapsing into each other before anything interesting can happen. And knowing this changes how you feel when you touch something. The solidity under your fingertips isn't really solidity in any classical sense. It's quantum pressure, electrons refusing, by the rules of their wave-like nature, to occupy the same space at the same energy level. What feels like hardness is actually a boundary written into the structure of information itself. That word, information, kept creeping into the conversations of the physicists working through all of this, not as a metaphor, as a technical description of something real, because the new framework they were building didn't describe where particles are. It described what can be known about particles. And that distinction, subtle as it sounds, turned out to be the sharpest edge in all of physics. The framework had a name now: quantum mechanics, and at its center was a mathematical object called the wave function, an equation that evolves smoothly and predictably over time, tracking every possible state a system could be in and assigning each state a probability. The wave function doesn't say where the electron is. It says how likely you are to find it in any given place if you look. And before you look, those probabilities are all equally real. The electron isn't hiding in one location while you're not watching. It genuinely occupies all its probable locations simultaneously, each one a real branch of its physical existence. existence, until the act of measurement forces a single outcome. This is called superposition, and it is the single most counterintuitive and most thoroughly verified fact in all of science. A quantum system holds multiple states at once, not as an approximation, not as a gap in knowledge, but as a precise physical description of reality. A particle can spin in two opposite directions simultaneously. A system can be in two energy levels at once, and a quantum bit, the basic unit of quantum computing, can be 0 and 1 at the same time, not switching between them rapidly, not averaging them, but genuinely, mathematically, physically both. The classical bit you're used to, the one underlying every phone and laptop and server in the world, must choose. It is always exactly 0 or exactly 1. The qubit refuses to choose until forced, and in that refusal lives a kind of computational power that has no classical equivalent, a parallelism so deep that it isn't really parallelism in the usual sense at all. It's something new. But superposition, strange as it is only the beginning of how strange things get. Because when two quantum systems interact, something happens between them that even the physicists who discovered it couldn't quite believe. Something that doesn't just challenge classical intuition, something that breaks the very idea of separation itself. Two particles can touch for a fraction of a second and then be separated by the width of a galaxy, and measuring one of them will instantly determine the state of the other. Not after a delay, not through any signal, instantly. And I mean that word literally, with no softening or exaggeration. This is not a metaphor for a close connection. It is a physical fact that has been tested in laboratories with increasing precision for decades and has never once failed to hold. The phenomenon is called entanglement, and the reason it breaks the idea of separation is not that the particles are secretly connected by some invisible wire. It is that separation, in the quantum world, is not the fundamental thing we assumed it was. Let me explain how it actually works, because the popular version usually gets something important wrong. When two particles become entangled, their wave functions merge into a single shared wave function. They are no longer two separate systems with individual states. They become one system with one state, a state that happens to be distributed across two locations. So when you measure one particle and its superposition collapses to a definite value, the other particle's part of that shared state collapses too, because they were never really separate to begin with. There is no signal traveling between them. There is no hidden message passing through space. The correlation is instant because the two particles are, in a deep mathematical sense, still the same thing. And this is where Einstein drew the line. He believed that two things in different locations must have separate, independent realities, that what happens here cannot instantly affect what happens there. He called the alternative spooky action at a distance, and he said it with the tone of someone identifying an obvious absurdity that would soon be cleared up. It was not cleared up. It was confirmed over and over and over again, with photons, with electrons, with atoms, with increasingly large and complex systems. The entanglement holds, the correlations appear, and the only way to explain them without accepting non-locality is to invent a complicated hidden structure that turns out to be impossible to construct without contradicting other things we know to be true. The universe chose non-locality. Einstein was wrong, and the person who proved it most rigorously didn't do it with a particle accelerator or a billion-dollar detector. He did it with math, a simple inequality, a boundary that any locally realistic theory must stay within, that entangled particles consistently cross every single time. The gap between what local realism predicts and what entangled particles actually do is not small. It is not ambiguous. It is wide enough that every serious physicist accepts the conclusion. The world is not locally real in the classical sense, and sitting with that fact, really sitting with it, feels like the floor quietly dropping away beneath everything you thought you understood. Now here's the part that makes this more than just an exotic curiosity about particles in a lab. Because once you know that entanglement is real, that superposition is real, that quantum systems genuinely hold multiple states simultaneously until forced to choose, the next question writes itself. Can we use this? And the answer is yes, in ways that are already changing the world and will change it far more dramatically in the years ahead. Go back to the beginning of this story, that particle traveling through both openings at once, leaving an interference pattern that no classical object could produce. That behavior is not a glitch, it is a resource. A quantum system in superposition is doing something that no classical system can replicate, exploring multiple possibilities simultaneously in a way that is physically real, not just conceptually convenient. And when you combine superposition with entanglement, something remarkable happens to the idea of computation itself. A classical computer processes one possibility at a time. It checks one path, gets an answer, moves to the next path, gets another answer, works through the list. Fast computers do this faster. Parallel computers split the list into chunks, but the fundamental mode is the same. One answer at a time, one branch at a time, one definite state at a time. A quantum computer works differently in its foundations. Its basic unit, the qubit, exists in superposition, holding both 0 and 1 simultaneously. 2 entangled qubits hold 4 states at once, 3 hold 8, 10 hold over 1,000. 50 qubits in full entangled superposition hold more simultaneous states than there are atoms in a human body. The computational space grows exponentially with each qubit added, and a quantum algorithm can explore that entire space in a single operation in a way that has no classical equivalent. This doesn't mean quantum computers are faster at everything. They aren't. For most everyday tasks, a classical computer is perfectly fine, and a quantum computer would be overkill of a kind that doesn't even help. But for specific problems involving vast numbers of interacting possibilities, quantum computers don't just solve them faster, they solve them in a fundamentally different way that classical machines cannot replicate at any speed. Factoring enormous numbers, simulating the behavior of molecules for drug discovery, optimizing systems with enormous numbers of variables. These problems are not just hard for classical computers, some of them are effectively impossible. And the reason they become possible for quantum systems is the same reason a particle passes through both openings at once. The universe, at its core, computes quantumly. We are just finally learning to do the same. But there is a catch, a serious one, and it sits right at the heart of why building a quantum computer is one of the hardest engineering challenges in human history. The catch is that quantum states are the most fragile things that exist in the known universe. And I'm not using fragile loosely. I mean that a quantum superposition can be destroyed by a single stray photon, by a vibration smaller than the width of an atom, by a tiny fluctuation in temperature, by anything at all that carries even the faintest trace of information about the system's state into the surrounding environment. The moment the environment learns anything about which state the qubit is in, the superposition collapses. Gone. Not degraded, not weakened. Gone. Instantly and completely. Replaced by a single definite classical state that carries none of the quantum advantage you were trying to use. This collapse has a name, decoherence, and it is the central villain of every quantum computing laboratory on Earth. Think about what this means in practice. You are trying to build a machine that performs calculations using states that must remain perfectly isolated from the entire rest of the universe for long enough to complete the computation. In a universe that is constantly, relentlessly, in every direction, trying to interact with everything. The engineering required to achieve even a few seconds of coherence in a system of meaningful size is staggering. Quantum processors are cooled to temperatures colder than deep space because thermal vibrations carry information, and information destroys superposition. They are shielded from electromagnetic fields with layers of specialized materials. They are suspended on isolation platforms to eliminate mechanical vibration. And even after all of that, qubits still decohere. Errors still accumulate. The race is not just to build bigger quantum systems, but to build them with error correction fast enough and precise enough to outpace the decoherence. And the error correction itself is quantum mechanical, which means it has to be done without measuring the qubits directly, because measuring them would collapse their states. So you correct errors in quantum systems by asking the system careful, indirect questions that reveal whether an error occurred without revealing what state the system is in. This is a level of engineering subtlety that has no parallel anywhere in classical technology. And yet, despite all of this, it is working. Imperfectly, noisily, at small scales, but working. Quantum processors have already performed specific calculations that would take the most powerful classical supercomputers longer than the current age of the universe to replicate. This milestone has a name too, quantum advantage, and it has been crossed. The era of quantum computing is not coming. It is here, in its early and awkward infancy, but here. The question now is not whether quantum computers will work. It is what happens to the world when they work well. What happens to encryption for a start? And this is where the story stops being purely about elegant physics and starts being about something that affects every person who has ever sent a private message, made an online payment, or stored anything sensitive on a connected device. The security of almost all modern digital communication rests on a single mathematical fact. Multiplying two large prime numbers together is easy. Factoring the result back into its two original primes is, for a classical computer, effectively impossible at the scales used in real encryption. A number with hundreds of digits would take a classical machine longer than the universe has existed to factor through brute force. This asymmetry between easy multiplication and hard factoring is the lock on which modern cryptography is built. A sufficiently powerful quantum computer running a specific algorithm can factor those numbers in a manageable amount of time. Not instantly, not with today's hardware, which is still too noisy and small, but with the hardware that serious projections suggest is coming within the next decade or two. The lock breaks. Every encrypted message ever recorded and stored, every private key ever generated, every certificate securing every website becomes vulnerable in principle. Governments and intelligence agencies are not waiting for this to happen. They are preparing now, stockpiling encrypted communications with the intention of decrypting them later when the tools exist. This practice has a name among security researchers: harvest now, decrypt later. And it means that data considered safe today may not remain safe in the future, which means the transition to quantum-resistant encryption is not a future problem. It is a present one. But here is the twist that makes this more than just a security arms race. The same quantum mechanics that threatens classical encryption also provides the foundation for a completely new kind of security, one that doesn't depend on mathematical hardness at all. Quantum cryptography uses entangled particles to distribute encryption keys in a way that makes interception physically detectable, not computationally hard to detect, physically impossible to hide, because intercepting a quantum key requires measuring the particles carrying it. Measuring them collapses their superposition and introduces detectable disturbances. The eavesdropper leaves a mark written into the laws of physics itself, a mark that cannot be erased or disguised. The security comes not from a mathematical problem that might one day be solved, but from a physical law that cannot be repealed. And this is the pattern that keeps emerging the deeper you go into quantum mechanics. Every limitation it imposes on what can be known comes paired with a capability it enables that nothing else can match. Which means the question of what quantum mechanics takes away is always also the question of what it gives back in return. And what it gives back next is stranger than anything we have covered so far. What quantum mechanics gives back next is the ability to measure things that should be physically impossible to measure, and I don't mean that loosely. I mean that there are detectors operating right now that observe phenomena so faint, so buried in noise, so far below what any classical instrument could resolve, that their existence would have seemed like pure fantasy to physicists working even half a century ago. The connection to everything we've covered is direct. Superposition and entanglement aren't just computational tools. They are measurement tools, and the way they improve measurement comes from the same place as everything else in quantum mechanics, from the fact that quantum systems carry information about their environment in ways that classical systems simply cannot. Here is a concrete example that makes this real. Imagine trying to weigh something so light that the act of shining a light on it to see it pushes it around. This is not a hypothetical problem. It is the actual challenge faced by the most sensitive force detectors ever built. Classical light, even a single photon, carries momentum. When it bounces off a mirror in a precision instrument, it gives that mirror a tiny kick. That kick is random, unpredictable, and at the scales required for the most sensitive measurements, it drowns out the signal you are trying to detect. Quantum optics offers a way around this. By preparing light in a special quantum state where the uncertainty is squeezed, redistributed from the variable you care about into a variable you don't, you can make measurements that violate what classical physics would set as the absolute limit of precision. The uncertainty doesn't disappear. Quantum mechanics doesn't allow that, but it moves. You push it out of your way, and the result is instruments of extraordinary sensitivity. sensitive enough to detect gravitational waves, ripples in the fabric of space itself produced by events of almost incomprehensible violence happening at distances of hundreds of millions of light years. The detectors that catch these ripples are kilometers long. They split a laser beam, send the two halves down perpendicular tunnels, bounce them off mirrors, and recombine them to look for interference. When a gravitational wave passes through, it stretches space in one direction and compresses it in another, changing the relative length of the two tunnels by a distance smaller than 1,000th the width of a proton. To detect that, the instruments must use quantum states of light to push their sensitivity past the classical limit. Quantum mechanics is not just the thing being detected, it is the tool doing the detecting. And the events being detected, collisions between black holes, mergers of the densest objects in the universe, are themselves described by a theory that quantum mechanics has not yet fully absorbed. That tension between what quantum mechanics enables us to observe and what it still cannot fully explain is exactly where the story goes next. Quantum mechanics explains atoms with breathtaking precision, but break down when gravity becomes extreme. And nowhere in the universe is gravity more extreme than inside a black hole. A black hole is a region where gravity is so strong that not even light can escape once it crosses a boundary called the event horizon. Beyond that boundary, the equations of general relativity break down completely, predicting a point of infinite density that every physicist on Earth agrees is not a real physical object, but a sign that the theory is being pushed past where it works. Quantum mechanics needs to take over. But when you try to apply quantum mechanics to the extreme conditions near a black hole, the two theories produce results that contradict each other in a way that is not just technically inconvenient, it is philosophically catastrophic. Here is the specific contradiction. Quantum mechanics has a rule, one of its deepest and most unbreakable rules, that information cannot be destroyed, not transformed, not hidden, not scrambled beyond recovery, but destroyed. The total information content of a closed system is conserved, always, the way energy is conserved. It is a law. Now consider what happens when something falls into a black hole. It carries information about its state, its composition, its history. The black hole swallows it. Over an enormous span of time, the black hole slowly radiates energy and shrinks, a process described by combining quantum mechanics with the geometry of curved space-time. Eventually, the black hole evaporates completely, and the radiation it emits during this process appears to be perfectly random, carrying no trace of the information that fell in, which means the information is gone, which quantum mechanics says is impossible. This is not a minor technical puzzle. It is a direct collision between two frameworks, each of which is the most precisely tested theory in its domain, producing an answer that cannot be right. Something fundamental is wrong, or missing, or both, and the attempt to resolve this has led physicists to a proposal so radical that the first time most people hear it, they assume it must be a mistake. The proposal says that everything happening inside a volume of space, every particle, every interaction, every bit of information about every event, can be completely described by what is happening on the surface surrounding that volume. That three-dimensional physical reality might not be the fundamental layer, that it might emerge from a two-dimensional description, the way a hologram produces a three-dimensional image from a flat surface. That depth itself, the experience of being inside a space with volume, might be a kind of appearance generated by something that is, at its root, a flat sheet of quantum information. And the reason serious physicists take this seriously is not because it sounds profound. It is because the mathematics works. The description on the surface and the description of the interior match with a precision that cannot be coincidence. Something real is being captured here, something that points toward a deeper layer of reality that neither quantum mechanics nor gravity taken alone can fully see. If three-dimensional space might be a kind of projection from something flatter and more fundamental, then the experience of being somewhere, of having a location, of existing inside a volume with depth and distance, might itself be something that emerges rather than something that simply is. That idea sits at the edge of what current physics can say with confidence. But there is something closer to home, something already built and already working, that illustrates the same principle in a way you can hold in your hand. Your phone knows where you are, not approximately, not within a city block, within a few meters, updated continuously, using signals from satellites orbiting hundreds of kilometers above the surface. The system behind this is one of the most precisely engineered things humanity has ever built, and it works in ways that almost nobody realizes because of quantum mechanics and because of the warping of time itself. Here is how. The satellites carry clocks, not the kind of clock on your wall, atomic clocks, clocks that keep time by counting the oscillations of electrons as they jump between energy levels inside atoms, transitions so regular and so stable that the clock accumulates less than a second of error across timescales far longer than recorded human history. The signal from these clocks tells your phone not just where the satellites are, but exactly when each signal was sent. Your phone measures the tiny differences in arrival time from multiple satellites and uses those differences to calculate exactly where on Earth you must be standing for all the numbers to be consistent. The precision required is extraordinary. A timing error of even a fraction of a microsecond translates into a positional error of hundreds of meters, which means the clocks have to be right, not just to a second, not just to a millisecond, but to within billionths of a second, continuously, for years. And here is where it gets strange. The satellites are moving fast relative to the ground. According to relativity, moving clocks run slower. The satellites are also higher up, in a weaker gravitational field. According to relativity, clocks in weaker gravity run faster. These two effects work in opposite directions and do not cancel out. The net result is that satellite clocks, left uncorrected, would drift by dozens of microseconds per day relative to clocks on the ground. Dozens of microseconds per day translates into kilometers of positional error per day. So every satellite in the navigation network runs its clocks with a built-in correction, calculated from relativistic equations, applied continuously, invisibly, every time you check your location. Quantum mechanics provides the clock, relativity corrects it, and the fact that both corrections are necessary, simultaneously, in a device that fits in your pocket is one of the most quietly remarkable things in the modern world. Two theories that contradict each other at the extremes, that physicists are still working to reconcile, are being used together every day to tell you where to turn. The contradiction at the cosmological edge doesn't stop the practical cooperation at the human scale, but that practical cooperation also makes the unresolved contradiction feel more urgent. Because if the two theories are incompatible at the foundations, and yet both are clearly describing something real, then neither is the final answer. There is something beneath both of them, and the search for that something has produced ideas about the nature of time itself that make everything else in this story feel almost conventional by comparison. Time feels like the most obvious thing in the world. It moves forward. It flows at a steady rate. Everyone experiences the same moment simultaneously. You don't need to be a physicist to feel certain about these things. They are baked into every language, every calendar, every memory, every plan, and every single one of them is wrong. Not approximately wrong, not wrong in edge cases, structurally, fundamentally wrong, in ways that quantum mechanics and relativity have now confirmed beyond any serious dispute. Time does not flow at a steady rate. It runs slower near massive objects and faster far from them. It runs slower for things moving quickly and faster for things moving slowly. There is no universal now. Two observers moving relative to each other will disagree about whether two distant events happen simultaneously, and both will be right, because simultaneity is not a fact about the universe, but a relationship between an observer and a reference frame. This is not a philosophical position. It is a measured, tested, GPS-corrected, experimentally verified description of how time actually works. But quantum mechanics adds a layer to this that even relativity doesn't prepare you for, because quantum mechanics says that the uncertainty principle applies to time and energy the same way it applies to position and momentum. You cannot simultaneously know, with perfect precision, both how much energy a system has and exactly when it has it. This is not a limitation of measurement technology. It is a structural feature of the universe, as fundamental as the fact that waves don't have sharp edges. And this uncertainty has physical consequences. Empty space, because of this principle, is not actually empty. It seethes with brief fluctuations, pairs of particles blinking into existence and vanishing again too quickly for any direct detection, but leaving measurable traces in the forces between objects and in the behavior of light. These fluctuations are real. They have been measured. The force they produce between two closely spaced metal plates, a pressure pushing them together from outside where the fluctuations are suppressed, is experimentally confirmed to exist. The vacuum is not nothing. It is a roiling quantum field, and the energy locked inside it is so enormous that one of the deepest unsolved problems in physics is explaining why the universe expands at the rate it does, rather than being ripped apart instantly by the energy of empty space. Quantum mechanics predicts that energy. The prediction is off by a factor so large it has no name in ordinary language. Somewhere between the quantum description of the vacuum and the gravitational behavior of the universe at large scales, something important is missing, something that no current theory captures, and finding it will require rethinking not just physics, but the deepest assumptions about what time, space, and existence actually are. The answer, if there is one, almost certainly lives somewhere in the territory where quantum information and the structure of space-time meet, which is exactly where the next part of this story goes. The territory where quantum information and space-time meet begins with a rule so absolute that physicists treat it the way engineers treat the laws of thermodynamics. You cannot copy an unknown quantum state, not with better technology, not with more resources, not ever. This is called the no-cloning theorem, and it falls directly out of the mathematics of quantum mechanics, with no exceptions and no workarounds. And at first it sounds like a limitation, like something quantum mechanics is taking away. But follow the consequence, and it becomes something entirely different. It becomes a guarantee. Here is why it matters. In classical information, copying is trivial. You copy a file, the original and the copy are identical, and nothing in the process reveals whether either version was tampered with. Quantum information cannot work this way. If someone intercepts a quantum signal and tries to read it, the act of reading disturbs it, because reading requires measuring, and measuring a quantum state collapses its superposition. The interceptor cannot then make a perfect copy to forward along, because copying an unknown quantum state is forbidden by physics. So the act of eavesdropping leaves a physical trace that cannot be erased. The disturbance is not a side effect that clever engineering might eliminate. It is structural. It is written into what quantum states are, and this transforms the idea of secure communication completely. Classical encryption is a race between the person hiding the message and the person trying to break the code. Quantum communication is not a race at all. It is a one-sided physical law. The security comes not from a problem being hard to solve, but from a process being impossible to perform without leaving evidence. This has already been demonstrated in real networks, not just in laboratory conditions, but in fiber optic cables running between cities and in experiments using satellites to distribute quantum keys across distances of thousands of kilometers. The technology is early, expensive, and limited in scale, but it works. And it works because nature enforces it, not because any human designed a clever enough system. Now take that idea, that information in quantum mechanics is not just a description layered on top of physical reality, but something that physical laws actively constrain and protect, and push it further. Ask what information fundamentally is. In classical physics, the answer is almost casual. Information is a pattern, a sequence of states, something you write down or transmit or store. It is defined relative to a system and an observer, but has no independent physical weight. Quantum mechanics disagrees with this picture in a way that becomes more radical the longer you sit with it. In quantum mechanics, information is not a label we attach to physical states. It is the substance those states are made of. The wave function of a system is not a summary of what the system is doing. It is a complete description of every physically real thing about that system. Change the information, and you change the reality. Preserve the information, and you preserve the physics. This is why the no-cloning theorem exists, why the information paradox in black holes is a crisis rather than a curiosity, and why the holographic proposal feels like more than a metaphor to the people working on it. If information is the fundamental layer, then the question of what the universe is made of gets a new and unsettling answer. Not particles, not fields, not space and time in their familiar forms. Patterns of relationship, evolving according to quantum rules, giving rise to everything we see and touch and measure as a kind of consequence. The patterns of relationship that give rise to everything we experience include, remarkably, the experience of being uncertain. And quantum mechanics has something very precise to say about uncertainty, something that goes much further than the everyday meaning of the word. We covered earlier that measuring a quantum system changes it, but the uncertainty principle adds something deeper than that. It says that certain pairs of properties are not just hard to measure simultaneously. They are impossible to define simultaneously with precision, because they are linked by the mathematics of waves in a way that makes sharpness in one direction produce blurring in another. Think of it this way. A musical note has a pitch, which corresponds to a frequency, and a moment in time when it sounds. A perfectly pure pitch, a single exact frequency with no variation, would have to ring forever, with no defined start and no defined end, because a wave with a single frequency has no localization in time. A sound with a perfectly defined start and end, a sharp click, contains a spread of frequencies, not one pitch, but many blended together. You cannot have both a perfectly defined moment and a perfectly defined frequency at the same time, because these properties are mathematically coupled in the wave description. Quantum particles obey the same coupling: position and momentum, energy and time. You cannot sharpen both simultaneously, not because measurement is clumsy, but because the universe is wave-like at its foundations, and waves don't permit it. What changed everything is that physicists learned to treat this not as a wall, but as a dial. Squeeze the uncertainty in one direction, and it spreads in the other. If you need to know energy very precisely and can tolerate less precision in timing, the mathematics allows you to redistribute the uncertainty that way. This is called quantum squeezing, and it is not theoretical. It is used in the most sensitive instruments ever built, instruments that have to contend with quantum fluctuations of light and mirror motion as practical engineering challenges, not abstract concerns. The gravitational wave detectors we mentioned earlier squeeze the quantum noise in their laser light so that the measurement they care about, the change in the relative length of two tunnels, becomes more precise than any classical light source could allow. They are borrowing certainty from a variable they don't need in order to sharpen the variable they do, and what they detect with that borrowed certainty is extraordinary. The collision of two black holes, each dozens of times the mass of the sun, merging in a fraction of a second and releasing more energy than all the stars in the visible universe emit in that same fraction of a second, produces a ripple in the fabric of space-time that, by the time it reaches Earth, distorts the distance between two mirrors by less than 1,000th the width of a proton. That is the signal. That is what gets measured. And the only reason it can be measured is that a team of engineers understood quantum uncertainty well enough to move it out of the way. The universe spoke in a whisper, and humanity, using quantum mechanics as the ear, heard it, which raises the question of what other whispers are still out there, waiting for instruments precise enough and theories deep enough to catch them. The whispers the universe sends us are written in a language that took humanity over a century to learn to read. And the most unsettling thing about that language is what it says about the nature of information itself, which is exactly where we left off. We established that quantum information cannot be copied and cannot be destroyed. These two constraints together create something extraordinary. They mean that everything that has ever happened, every interaction, every collision, every quantum event since the beginning of time, left a permanent and uncopyable record woven into the state of the universe. Nothing was ever truly erased. The universe keeps accounts with a precision that no classical ledger could match, and this changes the meaning of the word reality in a way that is hard to fully absorb, because if information is never lost and never duplicated, then the universe is not just a collection of objects moving through space. It is a record, a continuously evolving, perfectly conserved record of every relationship that has ever existed between every particle that has ever interacted. The objects are almost secondary. What is primary is the pattern of connections between them, the web of correlations built up through every entanglement, every measurement, every interaction across all of time. And here is the thing that physicists who work in this area find most striking. When you describe the universe this way, as a network of quantum relationships rather than a collection of classical objects, space itself starts to look like something that emerges from those relationships rather than something that contains them. distance between 2 points might not be a fundamental fact about the universe. It might be a consequence of how strongly or weakly those 2 points are connected in the quantum information network. Two highly entangled regions behave as if they are close. Two weakly entangled regions behave as if they are far apart. And the geometry of space, the actual shape of the distances we move through every day, might be nothing more than a map of entanglement strengths projected into a form our senses can navigate. This is not a casual speculation. It is an active area of research with mathematical results that keep pointing in the same direction. The structure of space-time and the structure of quantum entanglement are not two separate things that need to be reconciled. They might be the same thing described from two different angles, which means the space you are sitting in right now, the distance between you and the nearest wall, the volume your body occupies, all of it might be a kind of readout of quantum information relationships that your brain interprets as geometry. You are not inside space. Space is inside the quantum information. And the reason this feels so strange is that our intuition was built for the readout, not for what generates it. We evolved to navigate the map. We never needed to understand the territory beneath it, until now. Everything we have covered in this journey began with a single particle that refused to choose a path until it was observed. And it ends here, with the possibility that the space those paths exist in is itself a consequence of observation, a consequence of quantum systems becoming correlated with each other and building up, through countless interactions, the texture of a world that feels solid and continuous and three-dimensional to the minds that evolved inside it. The particle at the beginning of this story was not just a curiosity in a physics lab. It was a crack in the wall between what seems real and what is actually real. And every idea we followed through that crack, energy packets, probability clouds, superposition, entanglement, decoherence, quantum computing, unbreakable communication, gravitational wave detection, the information paradox, the holographic structure of space itself, every single one of them came from taking that crack seriously, rather than plastering over it and going back to comfortable certainty. The universe did not owe us an intuitive explanation. It gave us a true one instead, and the true one is far stranger and far richer than anything the classical picture could have produced. Consider what that means for how we approach what we don't yet understand. Every time in this story that someone insisted the current framework was complete, reality disagreed. Every time someone followed an uncomfortable result rather than dismissing it, a door opened. The heated object that should have radiated infinite energy led to quantum packets. The electron that should have spiraled into the nucleus led to the wave function. The entangled particles that Einstein called spooky led to unbreakable encryption and quantum computing. The black hole that seemed to destroy information led to the possibility that space itself is made of information. The pattern is consistent, and it is not subtle. Discomfort is the signal. The moment when the equation gives an answer that feels wrong is precisely the moment to lean in rather than look away, because the universe is not organized around human comfort. It is organized around something deeper, something that our instruments are only now becoming sensitive enough to touch, and our mathematics only now becoming precise enough to describe. And what we have found so far suggests that the deeper we go, the more connected everything becomes. Particles that seem separate share a single state. Regions of space that seem distant are close in the language of entanglement. Information that seems lost is preserved in a form we haven't learned to read yet. The universe, at its foundation, does not do isolation. It does relationship. Every boundary we draw between things turns out to be approximate. Every separation we assume turns out to be relative. And every certainty we hold about where things are, what they are, and whether they exist before we look at them, turns out to be a question the universe is still answering. That is not a reason to feel lost. It is the most honest description of where we actually are, standing at the edge of what is known, with better tools than any generation before us, asking questions that matter. So here is the one I want to leave you with. If nothing in the quantum world has a definite state until something interacts with it and forces a choice, and if the universe at its deepest level is a web of relationships rather than a collection of independent objects, then what exactly is doing the the observing when no observer is present? What collapsed the first superposition? What started the chain of interactions that built up the world we experience? Think about that. Drop your answer in the comments. I want to know where your mind goes. And if this kind of deep exploration into the nature of reality is what you want more of, subscribe and leave a like. It genuinely means the world, and it tells me to keep going.